Okay, so we're just talking about the basics of quadratic functions, which mostly you've seen before from Algebra 1. So just some vocabulary and then some different forms to write quadratic functions in, and then a couple of little application problems. So the vertex of a quadratic function is the minimum or maximum value. Right, so the vertex is the minimum or maximum. It is over here on the graph. That would be the vertex. So this is a minimum. If the parabola were going like that, then this would be a parabola that has a maximum. But currently it's a minimum value. The y-intercept is the point where it crosses the y-axis. Point where the graph crosses the y-axis. And what's important to know about a y-intercept, and this is true for any function, is that if it's crossing the y-axis, then that means x is equal to 0. So over here we have a y-intercept at y equals -5. And of course x-intercepts is where the graph crosses the x-axis. There's 3 commonly used synonyms for x-intercepts when we refer to really any graphs, but sometimes these are also called roots or zeros or solutions. So any of those 3 words is a synonym for x-intercept. Roots, zeros, and solutions. Zeros specifically because so if it's crossing the x-axis, that means y is equal to 0. So that's why we also call these zeros. But all 4 of these terms, x-intercepts, roots, zeros, and solutions, could be used interchangeably at any time. So you should know all 4. Also, fun fact, zeros is correctly spelled like this or with the E in between the O and the S. Yeah, fun stuff. All right, axis of symmetry, so that's the line that oh, let's label our x-intercept. So there's an x-intercept, and there's an x-intercept. And there's an x-intercept. So a quadratic function could have 2 x-intercepts, but we could also have a quadratic function that has no x-intercepts if the entire graph were above or below the x-axis. So if we had a graph that looked like this, we would have no x-intercepts. We could also have a graph that has a 1 x-intercept. So if the graph just had a vertex on the x-axis, so this has 1 x-intercept, this one has none, and the graph in red has 2. Okay, axis of symmetry, that is just the line that cuts the parabola in half. So that would be something like this on our graph. So it's in this case, it's a vertical line that cuts the parabola in half. And we use the symmetry of parabolas pretty frequently to graph them. So the domain of any quadratic function here, domain is always going to be all real numbers for any quadratic function. I don't know why there's 2 boxes. And the range of any quadratic function is, so a quadratic is either going to have a minimum or a maximum y value. So the range is always either going to be y is greater than the y value of the vertex, or y is less than the y value of the vertex. So that would be this if the parabola opened upwards. but it would be this if the parabola opened downwards. Okay, so there are three main forms that we write quadratic functions in. By the way, I keep using the words quadratic functions and parabolas. I want to point this out. So the type of function is called a quadratic function. The shape it makes is called a parabola. Okay, so standard form of a quadratic function looks like y equals ax squared plus bx plus c. And these values a, b, and c, and we've been dealing with standard form when we do those matrices problems. And these will control different things about the graph. So if you notice here, so here I have a quadratic function that is written in standard form. And if I change the value of a, well, a lot of things happen. But mostly, kind of zoom out to see it better. But mostly we see, and let's move b all the way to 0. So now we can mostly see that the graph is getting narrower as a increases and fatter as a decreases. And then if it becomes negative, then we also reflect over the x-axis. Or not necessarily, but, right? So it's changing the stretchiness of it. And then B is kind of moving it all over the place. So B doesn't have it has a predictable effect, but it's not one that we use often because there are better ways to write it, but it does move the vertex around. And then C is going to just move the graph up and down. So notice the y-intercept is always exactly equal to the value of C, right? So let's go ahead and record that. So we have, so A is going to change the width. So if A is bigger, then we get a steeper parabola. Steeper. Right. And if A is negative, then the parabola opens downwards. And then C is equal to the y-intercept. And this is true because if we remember, we said a y-intercept is when x is 0. So if x is 0 in this equation, then we have 0 squared times a plus b times 0. So the whole thing just goes to 0, and we're left with exactly c. Okay, on to vertex form. So vertex form is, we're rewriting a parabola, but now it's written using transformations rules, if you remember back from the first 6 weeks. So this minus h is going to shift the graph to the left or right, and the plus k is going to shift it up and down. And what that gives us, so the a is still going to do the same stuff, but h is going to equal the x-coordinate of vertex, and k is going to equal the y of the vertex. So if we look over here, now I have one that's in vertex form. And so now, like, A is still changing the stretchiness of it, but now it's not moving the vertex. And then H is just going to move it left and right. K moves it up and down. And one thing I forgot to say about standard form is in standard form, the x-coordinate of the vertex equals negative b over 2a. So that's a helpful thing to remember. All right, and then factored form. So factored form tells us think about what would happen here if x was equal to r1, right? So R1 minus R1 would be 0. 0 times anything would be 0. So R1 and R2 are the x-intercepts. So if we look at a parabola here, now it's in factored form. So A is still changing my width, but now, so it looks like it's moving it, but I want you to pay close attention to, so as I change R1 and R2, right now my intercepts are negative 1.6 and negative 1. And if I change R2 to be positive 5.5, now my intercepts have changed, right? So it's moving the vertex up and down because it's keeping the same, it's actually keeping the same width. It's just moving the vertex down and moving the x-intercepts across. And if A is negative, now we have parabolas that open down, and these are still changing the x-intercepts. So we'll talk about how to convert between the three forms later, but right now it's just good to know the three forms. Okay, so we can use these to write the equations of quadratic functions. So if we want to write one that passes through the point 3, 1 and has a vertex of 5, 7, since it gives us the vertex, the most convenient thing to do is use vertex form. So if the vertex is 5, 7, then I know that my graph is going to look something like a times x minus 5 squared plus 7. So I'm just plugging in 5 and 7 for, remember, vertex form was x minus h squared plus k, where h and k were the x and y of the vertex. So now, this is similar to when we find the equation of a line given a point. So I want to use the point 3, 1. So 3 is an x and 1 is a y. So I'm going to plug in 3, 1 for x and y, and then solve for what a is. Alright, so now I just have to simplify. So 3 minus 5 is, and I'll subtract 7 from both sides. So now I have negative 6 equals, now 3 minus 5 is negative 2, so a times negative 2 squared. And negative 2 squared is 4, so negative 6 equals 4 times a. And then divide both sides by 4. And we get a equals negative 3 over 2. So now my equation is y equals negative 3 over 2 times x minus 5 squared plus 7. So just like in problems with linear equations, you would plug in an x and y to solve for y-intercept. Here we just plugged in an x and a y to solve for the a value that makes it pass through that point. So now we're given one that has roots of 2 and negative 4. Remember, I said I'd use these terms interchangeably, so roots are the same as x-intercepts. And since it's giving me x-intercepts, the most convenient thing to do here is use factored form. So I have some number a times x minus 2 times x. So this would be minus negative 4, so that's just plus 4. And then same thing, I'm going to plug in my point 4, negative 8 for x and y. So y comes out to negative 8 when x is 4. So I plug it in both spots. So 4 minus 2 times 4 plus 4. So now negative 8 equals 4 minus 2 is a is 2. 4 plus 4 is 8. So that's negative 8 equals 16a. and a equals negative 1/2. So then my equation is negative 1/2 times x minus 2 times x plus 4. And you don't have to expand this. You don't have to FOIL it or box it and write it in standard form. A quadratic function can be written in any of these three forms. It could be converted between the three, but it doesn't ask us to write it in standard form. It just says write the equation of a quadratic function, which means I could use any of the three forms, right? So all three of these are acceptable. Okay, and now graphing. Obviously, we want to be able to graph these without a calculator because that's how you build. It's helpful, even before you use a calculator, it's helpful to know what these graphs are supposed to look like. So to graph a quadratic function, you always have to find the vertex. Makes your life so much easier. Because once you find the vertex, then you have reference points, and you can just put points on either side. So remember we said the x-coordinate is negative b over 2a. So negative 6 over 2 times 1, because this is a 1x squared. That's negative 3. So then the y-coordinate would mean I just find f of negative 3, and that's going to be the y of my vertex. So negative 3 squared plus 6 times negative 3 plus 2. That is 9 minus 18 plus 2. 9 minus 18 would be negative 9. Negative 9 plus 2 would be negative 7. That's dumb. So the vertex is negative 3, negative 7. So I say it's dumb because I didn't put enough spaces on this graph. So here's my vertex. And then to graph the other points, all I need to know is one other point, or two other points. And remember, this is my y-intercept. So I'm going to go ahead and put that point on here. So since this is my vertex and this is my y-intercept, I'm going to just sketch the, no, I don't want a line. I am going to sketch the right half of my parabola. And one thing I know about parabolas is that they have symmetry, right? This is my axis of symmetry because it always cuts through the vertex. So if I have a point that's over here 3 spaces to the right of the axis of symmetry, then I also have 3 spaces to the left. 1, 2, and again, I'm dumb, 3. So then there's the rest of my graph. Ta-da! Alright, so now one that is in factored form. So because it's in factored form, I immediately know that I have x-intercepts at x equals 2 and x equals 4. That gives me 2 of my points, right there and right there. Now, think about what we know about parabolas. There's an axis of symmetry that goes right between the x-intercepts, and that means my vertex is going to be x equals 3. Because it has to be right in between the two x-intercepts. So to get the y value, I'm just going to find f of 3. So 2 times 3 minus 2 times 3 minus 4. That's 2 times 1 times negative 1, which is negative 2. So then my vertex is at 3, negative 2. And then I can just draw my graph. All right.